Hey, my name is Kenneth Egelkrout, and for today's video, I like to discuss some of the earliest examples we have of modern probability theory. And my examples today are going to be coming from Christian Huygens, who was a student of Van Schooten at the time. And now, Huygens, he became particularly interested in probability theory during a visit to Paris in 1655, and he ended up actually writing a book about it, which he called On the Calculations of Games and Chances, which ended up being published just a couple of years later in Paris in 1657. Now, Huygens' work, it only contained 14 propositions and concluded with 5 different examples for the reader. But these propositions included ones that dealt with some of the Chevalier de Mere's problems, and these problems were mainly related to different gambling scenarios. And he gave very detailed explanations on the reasoning behind some of his solutions. And so, in particular, he showed how to calculate the value of a particular outcome. And so, in modern terminology, this is the value of chance. The value of chance is expectation, and the average amount that one would win if one played a game a certain amount of times. It's the amount a player would personally pay to have the privilege of playing an equitable game. And so let's turn our attention to his first proposition, which we'll be using to solve one of his example problems. And so to start, let's look at the first proposition of Huygens. And so he stated that to have equal chances of winning amounts, A or B, it's going to be worth A plus B over 2 to me. And so what this is essentially saying is if the first person wins, he receives A and his opponent B. And if the second wins, the payoffs are going to be reversed. And Huygens considered this to be an equitable game. So in modern terminology, since the probability of winning each A or B is going to be 1/2, the expectation for each play is going to be 1/2 A plus 1/2 B. And so this is Huygens' value of the chance. Now, moving down to his third proposition, where he says, to have P chances to win A and Q chances to win B, the chances of being equivalent is worth P times A plus Q times B all over P plus Q to me. This, coupled with his axiom where he stated, each player in an equitable game would be willing to risk the calculated fair stake and would not be willing to risk more. We're going to be using both of these in order to solve use his 11th proposition where he solves de Mere's dice problem. And so, moving on, in his 11th proposition, Huygens discusses de Mere's problem of the die, where he shows how to determine the number of times 2 dice should be thrown so that one could be willing to wager 1/2 A in order to win A if 2 6s appeared in a certain amount of throws. Now, let's move forward into how we actually solve this. So now suppose that one wins A when the 2 6s appear. Well then, on the first throw, an individual is going to have 1 chance of winning and 35 chances of also winning, but just winning 0, which is essentially equal to losing. And so the value of a chance on one throw in this case is going to be 1 over 36 times A. And so if the player now fails on the first throw, he then takes a second, whose value is naturally going to be the exact same of 1 over 36 A. Now, by the third proposition, the value of his chances of throwing a double 6 on these 2 throws is going to be 1A plus 35, 1 over 36, and then times A again. And this is going to be all over our P plus Q, which is going to be 1 plus 35. Now, when we solve for this, we're actually going to be getting 71 over 1,296A. And so this is going to be our chance of rolling a double 6 on just 2 throws. Now, when we increase it to 4 throws, if the player gets a double 6 on one of the first 2 plays, he wins A. And if not, he has a second pair of chances. And the value of this is going to be 71 over 1,296A. Now, since there are 71 chances of winning A on the first pair of plays, and therefore 1,225 chances of winning out of 1,296, then there's going to be 1,225 chances of reaching the second pair of plays, whose value is also going to be 71 over 1,296. And so by the third proposition, again, the chances of throwing a double six in 4 throws is just going to be 71A plus 1,225 times our 71 over 1,296A. And this is all going to be over 1,296. And when we solve for this, we're actually going to end up with 178,991 all over 1,679,616. So this is going to be the chance of throwing a double six in just 4 rolls. But as you can see, this is significantly less than the 1/2 A that we originally sought out to achieve. Now, while Huygens didn't provide any further calculations, we do know that he noted that one should next consider 8 throws, and then 16 throws, and then follow that by 24 and 25 throws. He noted that after 24 throws, the player is still going to be at a slight disadvantage on this bet of 1/2 A that we're looking for. Whereas once they pass this threshold value of 24 throws and achieve 25 throws, the player is actually going to possess a slight advantage. So the ultimate answer that we're looking for here is to throw this set of die 25 times in order to have an equitable game, according to Huygens. And so this whole general concept of probability theory from Huygens' perspective, this relates to modern mathematics in the sense that this is one of the first examples of probability theory that we have today. And its text on the calculations of games and chance, it served as the world's first and only introduction to probability theory, at least until the 18th century. And even then, its influence was felt by James Bernoulli. It continued on in James Bernoulli's work, wherein he incorporated his Huygens' actual work into his more extensive work on probability. And Bernoulli's work was called the Ars de Conjectandi of 1713. And so ultimately, for all these reasons, I find Huygens' work to be critical to the development of probability theory, and honestly, very integral to the advancement of modern mathematics. Without him, probability theory may not have been developed as quickly as it was.